So this worksheet is an extra conditional probability worksheet, and it's just to go over more in-depth conditional probability because it's a concept that a lot of people struggle with. Also, the tree diagram concept I think is really important on a lot of these. So let's just go through the questions. What I advise you do is I won't read every problem because I think you can read them. So I'm just going to go quickly through each solution here, and you can pause the video as I go through each problem. I would advise attempt the problem first and then watch my solution. Also, if you look at the completed conditional probability worksheet, this version is completed and posted. At the very bottom, all the answers are also, or will be, they're not here, but they will be listed. So that's something else that you can do as well. Okay, so let's see this. So the first one is we want to find the probability that in 1A, probability that if two perfectly balanced coins are tossed once, find the probability that both coins show a head given the first shows a head. And I think the simplest way to do this is just think of the sample space. So we can have heads, tails, heads, tails, tails, heads, and tails, tails, right? These are the four possibilities. So what is the probability that both coins show a head given the first shows a head? Well, if we're given the first shows a head, we only have to look at the first two, and one of those two have both coins showing a head. And then 1B, find the probability that both are heads given that at least one of them is a head. Well, for at least one heads, that would be these three, and one of them has both of them showing heads. So a lot of people make this problem more difficult than it is, but that's it. If you just look at the sample space, you can pretty easily get the probabilities. Okay, number 2, I would advise using a tree diagram for. So we have this city with male and female. There's 40%, 60%. There's gum chewers, non-gum chewers. And the gum chewers are, it says 50% of the males chew gum, means 50% do not, and then 30% of the females chew gum, 70% do not. So we want to find the probability that a person that chews gum is male. So in other words, our probability we're trying to find is actually if they're male. And we're given, because it's find the probability that a person that chews gum. So that means we're given that they chew gum. So this is the probability of male and a gum chewer. That's a G. It's a poorly written G. Divided by the probability of being a gum chewer. So this is going to be 0.4 times 0.5, because that's the probability of being male and a gum chewer. And then we divide by 0.4 times 0.5, because this is the probability of being a gum chewer. But they can also be a gum chewer if it's 0.6 times 0.3. Okay, so that's the calculation there. And the answer to this one is 0.5263. Okay. All right, number 3. So we have this box that contains 3 white balls, and whenever you have a balls in a box, or it might be marbles in a jar, it might be blocks in a box, whatever it is, okay, it's always best to put a subscript next to each color, because even though there's 3 white balls, they're not all the same ball, right? There's 3 distinct white balls. So it's very important that you write them out as such. Okay, so if we get 2 balls are drawn from without replacement, find the probability that. You could do a tree diagram for this one, but I would advise, let's write out the sample space, which is going to take a little bit of time, but it's going to be worth it in the end. So if we're drawing 2 balls, so we can get the first white one, the second white one, the first white one, the third white one, the first white one, the first black one, the first white one, the second black one. And then we can start with the second white one. So the second white one, the third white one, or actually the first white one. And these are not the same, right? Just so you know that. You take the second white one and then the first white one, whereas this one we draw the first white one first. So they are different. So white 2, white 3, white 2, black 1, white 2, black 2, white 3, white 1, white 3, white 2, white 3, black 1, white 3, black 2. And then we start with the black ones. Black 1, white 1, black 1, white 2, black 1, white 3, black 1, black 2, black 2, white 1, black 2, white 2, black 2, white 3, black 2, white, or black 1. All right, so now 3A. What is the find the probability that the second ball is black given the first ball is black? So first denominator, always divide by what you're given. How many possibilities have the first ball black? That's all 8 over here. Of those 8, how many have the second ball as black? 2. The answer is 1/4. 3B. The second ball is the same color as the first. There's no given here, so we have 20 possibilities. How many have the second color the same color or the same color as the first? 1, 2, 3, 4, 5, 6. Just realized you can't see my mark. So 1, 2, 3, 4, 5, 6, 7, 8 out of 20. Which simplifies to 2/5. And then 3C, the first ball is white given the second ball is white. So how many have the second ball as white? 1, 2, I'll put a green mark next to these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12. And then how many of those have the first ball white? 1, 2, 3, 4, 5, 6. Looks like the answer is 1/2. So you could use a tree diagram with this, and I'm not going to go through that solution, but if you just write out the sample space and just look at the sample space and think about, you know, what the possibilities are, I mean, I think it's easier to do it that way, even though it's a little bit more upfront work. All right, number 4. So we have Kevin. He's a poker player. He's dealt a pair, decides to flip a coin. So you get heads or tails if you flip a coin, which is a 50% chance each. And then heads, he keeps a pair. If he keeps the pair, his chance of improving is 0.287. Oops, reverse these. 0.287. And his chance of improving if he gets tails is 0.26. Right, because heads he keeps the pair and draws 3 cards. Yeah, and drawing 2. Yeah, okay. And you can draw the branch out here for not improving if you want, but we don't need to know that probability, because all we need to know is we want to find the probability that Kevin improves. That's all we care about. Well, there's 2 ways he improves. He gets heads, which is 0.5 chance times the probability of him improving if he gets heads. And then we add the probability of getting tails, which is also 0.5 chance times the probability of improving his hand if he gets tails. And so the probability of him improving his hand is 0.2735. All right. All right, number 5. Suppose that if a person with tuberculosis given a chest x-ray, the probability that his condition will be detected is 0.95. So we have tuberculosis people, not tuberculosis people, and then we have the condition being detected and not detected. That's what I'll do. So this is very similar to the infection problem that was in the notes. But it says 0.1% of people have tuberculosis. Now, key is percent. Percent. That's what a lot of people overlook. So that's only 0.001. And then the probability that it's detected is 0.95. Which makes this 0.05. and the probability that it's detected in someone without tuberculosis is 0.002. So this is the false positive rate, right? This is 0.998. So we want to find what's the probability that someone has tuberculosis if it is detected with the chest x-ray. Very similar to the problem that we have in the notes. So probability of tuberculosis and chest ray divided by the probability of just being detected. So the probability of it being tuberculosis and chest ray x-ray is 0.001 times 0.95. I just realized this is not going to fit. All right, so that's better. So tuberculosis and chest x-ray detected in a chest x-ray is 0.001 and 0.95 multiplied together. And then the probability it's detected is 0.001 times 0.95. Notice this part is in the numerator is in the denominator if you're doing this correctly. And then 0.999 times 0.002. And the answer here is 0.3223. Okay. So not a good test again. You want to do better than this typically. So if the chest x-ray says you have tuberculosis, you really only have about a third of a chance of actually having tuberculosis. 6 is one of my favorite problems. I love 6 because people always get this wrong. So you have a box. Actually, you have 3 boxes. And one box contains 2 pennies, which I'm going to denote as P1 and P2. The next box contains a penny and a dime, which I'm going to denote as P3, just to distinguish it from the other 2 pennies. And a dime, and then I'm going to do the one with the 2 dimes as D2 and D3. So here's the thing. If a coin is taken out is a penny, what is the probability that the other coin in the box is also a penny? Well, let's try the sample space. So if I pull out this penny, the other coin is P2. If I pull out P2, the other coin is P1. If I pull out P3, the other coin is D1. If I pull out D1, the other coin is P3. If I pull out D2, the other coin is D3. And if I pull out D3, the other coin is D2. So this is the sample space. Now, you have to be careful about what you're given. If the coin taken out is a penny, so if we take out a penny, well, how many possibilities did we take out a penny? 3 possibilities. And of those 3 possibilities, how many have the other coin as a penny? The answer is 2/3. That's it. Again, you can use a tree diagram for this, but I think the simplest way to do this one is just think about the sample space. You can do this every time. All right, the last one is very useful if you use a table, actually. So whenever you have actual counts like this, I would strongly advise making a table. Okay, so we have 180 professors at this university. So we have a total, we have 180, and then we have PhD first. So I'm going to put PhD up here, and then I'm going to put research down here. And then yes, no, yes, no. Get my cursor out of the way so it's not quite as distracting. Okay, so it says there's 135 PhD degrees. 146 devote at least part of their time to research. And 114 of the 135 devote part of their time to research. So now it's you can fill in the rest of the table and answer the questions actually quite easily. So let's fill in the table first and then answer the questions. So this is going to be 32. This is going to be 21. This is going to be 45. This is going to be 34. And this is going to be 13. It should work both ways. So A, what's the probability they hold a PhD degree or devote part of their time to research? Well, there's 135 PhDs of 180, plus there's 146 out of 180 that devote part of their time to research. And then remember, for the and or, which is actually just an or, you subtract the overlap. So you have to subtract 114 over 180. And the decimal for that is 0.9278. Okay, part B, does not hold a PhD degree and does not devote any part of his time to research. So does not hold a PhD degree is, or does not hold a PhD and, so keyword is and, well, that is just the no, which is 13, so that's 13 out of 180, which has a decimal is 0.0722. C, will hold a PhD degree given he devotes part of his time to research. So if we know he devotes part of his time to research, which is this top column, there's 146 of them that devote part of their time to research, and 114 have PhDs, which is 0.7808. And then finally in part D here, will devote at least part of his time to research given he does not hold a PhD degree. So given no PhD degree, so there's 45 of those people. How many people research? 32. So that's 0.7111. So once you see the the table, I think it's a lot easier to actually answer the questions. All right, and that was the conditional probability worksheet.